Swayam Prabha. Digital India. Educated India.
We will discuss about vibrational non-equilibrium in this lecture. We will discuss about the concept of vibrational non-equilibrium and then we will move on to derive the vibrational rate equation. We have discussed about kinetic theory of gases during the last two lectures and we discussed that molecular collisions are necessary to initiate chemical reactions, but it is not only that. If we want vibrational energy of a gas to get excited and also change with time, such things can happen under molecular collision environment only, which means for excitation of vibrational energy as well as for inducing the chemical reactions, for both of them we need adequate number of molecular collisions. When we try to find the time rate of change of vibrational energy of the molecules, we need a vibrational rate equation. And the idea of rate comes in because we are talking about a non-equilibrium. It is not a steady state. That means the things are changing, the energy levels are getting altered, and if you allow enough time for adequate number of collisions to happen, then it will reach a state of equilibrium. But if all that is happening in a hurry and adequate number of collisions are not taking place, so that the vibrational energy keeps changing during the time we are observing the system, then we definitely need to look at the rate at which the vibrational energy is changing. So, keeping this in mind, let us try to work out a vibrational rate equation. We recall the energy level diagrams. We had drawn it for all possible energy modes: translational, rotational, vibrational, as well as electronic. And in general, all of them looked like a set of stairs. We started from a reference level and then we moved on to different higher levels. So, that was basically the concept of energy level diagram. Of course, here in this lecture we are going to concentrate on how things happen as far as the vibrational energy is concerned. We would need the vibrational energy level diagram indicating the quantized vibrational energy levels. So, we know already now that these levels are discrete, distinct levels of energy. That is what we mean by quantized. Vibrational energy mode is no exception, and we would be looking at a specific level. We will draw our attention towards a specific level, let us say I, where the energy level is small e I, and then we will be most interested to look at the next higher level and the next lower level when the vibrational energy exchanges take place. Particle collisions, which allow particles to move to and fro from the ith level to the immediately neighboring two energy levels, will only be considered. Therefore, the two neighboring energy levels are I minus 1, which is below, and I plus 1, which is just above. And due to the molecular collisions, if there is any outward movement of particles molecules or atoms. From the ith level, they can only go to the lower level I minus 1 by losing energy, or to I plus 1 by gaining energy. If they do move outward from the level I, it obviously means that the population at the ith level would decrease. On the other hand, if there is inward movement of the particles, again due to molecular collisions, where they move up from I minus 1 to I by gaining energy, or they move down from I plus 1 to I by losing energy, again that leads to population change, and this time it is population increase at the ith energy level. So, when we devise the vibration rate equation, we allow only these possible energy level interactions in our model. It does not necessarily mean that every time the energy exchanges will be such that they can just move between 3 such levels. Movement across higher levels are also possible, both upward or downward, but we are not accounting for that in this model. Let the initial particle population at the ith energy level be Ni. So, as you can understand, when we talk about equilibrium, then this population distribution would be purely defined from the Boltzmann distribution. But here, since it is non-equilibrium, we cannot use that theory per se. We have to accept the fact that the particle population is basically a function of time, and the population at the ith energy level will keep changing with time as long as it is non-equilibrium. Simultaneously, the neighboring levels will also see population change because of what you see at the ith level, because they are all interacting with each other, and through the rate equation we get an idea that how population keeps changing with time. Let us define a transition probability. We will indicate it with a nomenclature capital P suffix m comma n, and it is the probability that a particle at the mth energy level will jump to the nth energy level upon collision with another particle, where m could be greater than n, m could also be less than n. Transition probability is the number of transitions per collision per particle. We have to take note of the definition. Again, to reiterate, it is the number of transitions per collision per particle. Now, for a given collision between two particles, there is no certainty that a transition will definitely happen. It may need a lot of collisions between two particles, where one of the particles is fixed while the others would be varying. It may take a large number of collisions between this reference particle and its neighboring particles till the reference particle sees any transition. Therefore, there comes the issue of probability. Since a single transition from one energy level to another requires many collisions, the value of P m comma n is always less than unity. So, P m comma n is less than 1. Again, P m comma n is not equal to 0. Otherwise, no matter how many collisions took place, there would never be a transition. There would be no possibility of a transition, but that is not true. Therefore, it lies below 1, but again it is positive. When we are considering P m n with different m and n values, as we mentioned earlier, that m could be greater than n, in which case a transition is accompanied by a loss of energy due to particle collision. That is when the starting energy state or the energy level lies at a higher level than the ending energy level. It is just the other way around if m is less than n. Such a transition is accompanied by gain of energy due to particle collision. Now, we recall some result from what we learned in the kinetic theory of gases. I hope you recall about the single particle collision frequency, and this under root 2 also makes you recall that we are considering relative velocity in this situation. Also, because you do not have any subscripts here, for example, it is implied that it is a single species. So, finally, what you see over here in terms of pressure and temperature can be represented like this. We associate the single particle collision frequency with the transition probability, and we define an expression like this. So, we have multiplied the probability P m comma n with z. So, one of them gives a probability that how many transitions can take place after a particle collides with many, and the other gives us the count of collisions per particle per second. So, when you take a product, the transition probability of particle moving from quantized vibrational energy level m to n due to particle collisions, it actually gives us the transition per collision per particle, while the second term gives the collisions per particle per second. This provides a product which is number of transitions per particle per second. So, we have to be careful about what the product actually signifies, number of transitions per particle per second. Now, if we have n m number of particles in level m, we are putting the subscript m to specify a certain energy level, then the total number of transitions per second from m to n level is given by a product like this. We already had a product of P and Z. Now, we have multiplied the number of particles which are available at a particular energy level. So, by level we of course always imply energy level. Accounting for the possible transitions from and to the ith energy level, we can write the net rate of change of the population of the ith level as follows. So, now comes a very important form where we are seeing the term on the left hand side of this equation gives us the time rate of change of number of particles at the ith level. Now, we already understood that there could be an increase in particle count if there are particles coming in from the I plus 1th and I minus 1th level. There could be a decrease in particle count if particles are moving away from the ith level to I plus 1 or I minus 1. And these two sets of terms exactly model these two phenomena. P I plus 1 comma I times Z times n I plus 1 would indicate particles moving into particle level I from the energy level I plus 1. Similarly, P I minus 1 comma I Z n I minus 1 indicates particles which are moving into the energy level I from energy level I minus 1. So, these would increase the Ni count, and there is of course a rate involved with it, while here the remaining two terms, the third and the fourth term, they are accompanied by a negative sign because they lead to rate of decrease of Ni. And what is happening here? P I comma I plus 1 times Z times Ni gives you the number of particles per unit time which are moving out from level I to I plus 1, while P I comma I minus 1 Z Ni gives you the number of particles moving out of energy level I to I minus 1. The interpretation is very, very important. So, you should get used to this nomenclature, the expressions that we are using. The vibrational rate constant K m comma n is introduced now, which is nothing but the product of the probability and z. We have already handled this product earlier, but we did not introduce the vibrational rate constant earlier. We now do it. So, this is applicable for any of the 4 permitted transitions that we have included in our model, that is I to I plus 1 or I minus 1, and again I minus 1 or I plus 1 to I. This in all gives you 4 possible permitted transitions in our model. Again, remember, our model is based on certain assumptions and it does not account for all possibilities, but we are just trying to confine it to a simple framework at this point. On including the vibrational rate constant, the time rate of population change now can be expressed like this. It has a more simplified look, it has a more compact look, where you can just deal with the vibrational rate constants and the populations at the different energy levels, which are again instantaneous. This is called as the master equation for vibrational relaxation. This is a very important equation, and that is why we have boxed it. Now, let us think about the concept of relaxation time, which is a very important concept in physics. It is associated with some time delay, and here in this context it is the time delay in achieving vibrational energy level change through adequate number of molecular collisions, which are needed to bring about that change. We have been talking about this concept that all these changes, vibrational energy excitation or chemical reactions, all such changes have to be brought about with the assistance of molecular collisions, and that will not happen within a very short time. It takes a finite amount of time for the molecular collisions to happen at that level, so that these phenomena can take place, and in the process we have some kind of a delay. So, relaxation time talks about that delay. We will now recall some information, some data from statistical thermodynamics, which we have mentioned earlier, but it is a good time to recall about that, where we talk about the epsilon dash vibrational given by h nu in brackets n plus half, where n is vibration or vibrational quantum number, and the quantum number can vary from 0, 1, 2 onwards. The sensible vibrational energy, on the other hand, can be obtained from the epsilon dash expression by subtracting the epsilon 0, the 0 level energy, and then this corresponds to epsilon dash, while this corresponds to epsilon 0 for the vibrational mode, because the n is equal to 0 for the 0 level energy. Correspondingly, the epsilon vibrational equation comes out to be n h times nu. Now, this is a very important result which we will now require. This result will be plugged in suitably. So, let us see where it goes. Now, we will briefly recall about a result which has to deal with equilibrium. Though we are dealing with a non-equilibrium situation here, which keeps changing with time, which keeps the population to change with time, but it is a good time to recall the Boltzmann population distribution as a reference, where we have the population described across all possible energy levels which may be populated, with a star here to indicate equilibrium. And of course, we have the partition energy in the denominator of that expression. Now, if we were to apply the above equation to the energy levels I and I minus 1 and take a ratio of the particle number between these two energy levels, then what would result out of it? Let us try to work it out. So, Ni star by Ni minus 1 star will reduce to a form like this if you assume that these being immediate neighbor level energy levels, they may have identical redundancy levels. So, the Gj values could be identical or very close to each other, assuming that the equation would reduce to a form like this. And then if you substitute the expression for the epsilon vibrational that we just talked about for the ith level and the I minus 1th level, you have to just go back to the NH nu expression and substitute I and I minus 1 respectively to come to this index for E. It comes out to be minus H nu by kT. Similarly, if you were to take the energy levels I and I plus 1, because this is also of interest to us, and take a ratio, using a very similar approach, you would be able to come to an identical expression. Again, we assume that the Gj levels are identical for those two neighboring energy levels. In equilibrium, the number of transitions from energy level m to n is exactly balanced by the number of transitions in the opposite direction, that is from the energy level n to m. This would ensure that the equilibrium population distribution across the different energy levels would be maintained or sustained. Now, even if there are vibrational transitions, you do not end up seeing any net effect on the population distribution in a big way. This principle of reciprocal transitions between two energy levels, it is called as principle of detailed balancing. If we apply this principle between say two levels I and I minus 1, then that principle basically leads to an equality between two terms k I minus 1 I n I minus 1 star balancing k I minus 1 n I star. This is precisely the mathematical form for the logic that we just discussed verbally, that equal number of particles being exchanged between two neighboring energy levels, so that the overall population distribution does not see a change. Also, if you recall about this result which we have already seen and you plug it in here, then this is how it looks. K I minus 1 I will be equal to k I minus 1 into e to the power of minus h nu by kT. If we were to apply it between levels I and I plus 1, then let us see how it works. The balancing works like this in that case, and then again plugging in the relation that we had obtained earlier, we should be able to show that k I plus 1 is nothing but k I plus 1 I e to the power of minus h nu by kT. This we had already shown earlier, and that is exactly what we have used here. Now, the above two relations that we just saw, they involve reciprocal vibration rate constants between energy levels I and I minus 1 and I and I plus 1 respectively, and they are valid both under equilibrium as well as non-equilibrium flow in general. So, though we have borrowed partly from the Boltzmann distribution which is valid for an equilibrium situation, but when it comes to applying that concept in terms of reciprocal vibrational rate constants, then in principle it gets extended to non-equilibrium as well. It gets applied on an instantaneous basis. At every instant of time, we keep balancing the terms which are involved with the reciprocal vibrational rate constants. A result from quantum mechanics would be very useful at this point, which connects rate constants for higher energy levels in terms of transition from I equal to 1 to I equal to 0. So, that is basically the lowest possible energy level transition that we are talking about when you are moving from I equal to 1 to I equal to 0. So, that is basically the constant involved for that kind of a transition, and that can be connected with any higher level rate constant using the following equation, which is a very important one, very useful one, but it comes directly from quantum mechanics. We will just invoke it here. So, a transition from I to I minus 1 can be linked with the expression on the right hand side, I times k 1 comma 0. Note that if we replace I by I plus 1 in the above equation, we get another equation of this form, k I plus 1 I is equal to I plus 1 in brackets times k 1 comma 0. Why we mention it here is because we will soon see that that will be required for us. We now have a couple of equations which can be meaningfully combined, so that we can use them in the d n I dt equation. So, let us club them together. So, this is one lot which we indicate as A, and if we combine, then we get a form like this for k I minus 1 I in terms of k 1 0, and then there is another lot here which when clubbed together will give us another important equation here, which is k I plus 1 again in terms of k 1 0. Now, if you go and substitute these forms into the d n I dt equation, you see that term by term you are able to express them in a form where the individual instantaneous populations are represented along with the k 1 0 values, and some of the terms include the exponential term as well. Now, if you rearrange all the terms, some of them can be clubbed with the exponential part, the others do not need it, and every term has a common part coming from k 1 0. According to the above equation, as the population at the ith vibrational energy level changes, there would be change in vibrational energy content of the gas. For achieving that purpose, we would use the following equation of vibrational energy for unit mass of gas. So, the idea would be that from a population point of view, we bring in the energy perspective. So, we bring in a form like this, where we sum up the energy content coming from each energy level over all the levels, and we substitute the sensible energy for each level here, and it comes up as a summation like this. So, this is an important change which will come, which we will see reflected in the equation finally. So, when you take a time derivative of this equation, then it is expressed in terms of time derivative of the population distribution, and then if you rearrange the terms, you see a h nu k 1 comma 0 outside a summation which contains some expressions which apparently look a little complicated. They are not all that complicated, but we will not try to expand them in detail, but rather take a standard result which shows that these big expressions can be reduced to much simpler summations, and once we apply them here, we get reduced forms of the expression for the time rate of change of vibrational energy, and then we also come up with some summations which are easy to handle. For example, this summation just gives you the total population, while this summation you should be able to express it in terms of the vibrational energy by h nu. We proceed with this discussion and we come up with an expression like this for the time rate of change of vibrational energy. Since we are dealing with unit mass of the gas, therefore, n particles are contained in unit mass, and therefore, if you multiplied it with the Boltzmann constant, you should be able to get the specific gas constant. And here we just recall about something that we have visited earlier, that we had the partition function for vibrational energy, and then we had taken a partial derivative of that with respect to temperature at constant volume, and thereby we had come up with a form for the vibrational energy in terms of the derivative that we took of q, and a form like this was created. Now, we recall that that is basically the equilibrium vibrational energy that we came up with. So, we choose to express that as the vibrational energy under equilibrium, and we need to distinguish it from the vibrational energy which is at non-equilibrium. So, the one which is under non-equilibrium will be just expressed like this, E vibrational. We are not going to specifically show any nomenclature for the non-equilibrium part, but it is implied, while the equilibrium part will be specifically mentioned. So, once you do that and you substitute all the expressions that you have worked out, you come up with a very elegant expression here, where a difference between the equilibrium vibrational energy and the instantaneous non-equilibrium vibrational energy is there within brackets, and here is a term which has units of inverse of seconds. Thus, based on that, we introduce a time scale which is called as the vibrational relaxation time, and we define it by tau. That is introduced over here, and what we come up with is a very important equation, which is the vibrational rate equation that we set out to derive. Now, we will discuss more about this equation in the weeks to come. We just went through the derivation here. Let us conclude by saying that in this lecture we discussed briefly about vibrational non-equilibrium and the context under which it occurs, and we also discussed about the vibrational rate equation. We derived it at length, and we said that there are certain assumptions which are associated, and we will take all this up at greater detail when we revisit this equation in later lectures. Thank you.